Welcome to today's lesson on energy changes in simple harmonic motion. By the end of today's lesson, you should hopefully be able to describe the energy changes in simple harmonic motion, use the term total energy in terms of simple harmonic motion, and derive equations to calculate the kinetic, potential, and total energy of a system oscillating with simple harmonic motion. Let's start by looking at the mass on a spring oscillating system. So we start in the top position, which we will call A. The spring then moves through the origin to the bottom position B and back up through the origin to the top position A again. So let's see what different types of energy it has in these different positions. At position A, it has its maximum potential energy due to gravitational potential energy and zero kinetic energy. At the equilibrium position, it has its maximum amount of kinetic energy and its minimum amount of potential. And at the position B, it has its maximum amount of potential due to the energy stored in the spring. So let's have a look at the graph of these different energies in simple harmonic motion. So first of all, kinetic energy. At position A, it's 0. At position O, the equilibrium, it's a maximum. At position B, it's 0. At position O, it's a maximum again. And at position A, it's a minimum again. And this makes sense if we think about it in terms of the motion, the simple harmonic motion. At the maximum positions, we have a change in direction, so the velocity is 0. And at the equilibrium position, it's moving with no deceleration, no forces opposing it, and so it's moving at its maximum velocity. Right, onto the graph of potential energy. So at the top position, it has its maximum gravitational potential energy. By the time it gets to the equilibrium position, all of that gravitational energy has been converted into kinetic energy. Well, most of it has, if we're considering an ideal system. All of it's been converted. Down to position B, all that kinetic energy has been converted into elastic potential energy in the spring. It pulls it back up through the equilibrium position where it has its maximum kinetic energy and minimum potential, and back to position A where it has maximum potential from gravitational potential again. And onto total energy. So with total energy, we're going to look at a graph of kinetic energy and a graph of potential energy together. Hopefully you'll see that if we sum these at any given point, we're going to end up with the same value, and we call that value the total. So if we add in a line here representing the total energy, we can see it's a straight line. There's no variance with time. Obviously, this is assuming an ideal scenario where no energy is lost as heat or sound. So let's have a look at the equations for energy in simple harmonic motion. So our general equation for kinetic energy equals half mv squared. But for simple harmonic motion, we've said that V equals omega times root amplitude squared minus displacement squared. When we put that into the equation for kinetic energy, we end up with half m omega squared multiplied by the amplitude squared minus the displacement squared. We can use this to generate an equation for maximum kinetic energy. At the equilibrium position, the displacement is 0. So the maximum kinetic energy is half m omega squared times the amplitude squared. We're going to use this definition of maximum kinetic energy to generate an equation for total energy. As we discussed earlier, total energy is the sum of kinetic and potential energy. So at our equilibrium position, when potential energy is 0 and kinetic energy is a maximum, the total energy is half m omega squared multiplied by the amplitude squared. This holds true for calculating the total energy at any time and any position on the object's motion. Now we can use our equations for total energy and kinetic energy to derive an equation for potential energy. We take the total energy and subtract the kinetic energy from it, and we arrive at potential energy equals half m omega squared multiplied by the displacement squared. Let's look at how these equations relate to the graphs. So kinetic energy equals half mv squared. We're going to sum in our equation for velocity that we derived in the last lesson, and we end up with half m omega squared displacement squared multiplied by sine omega t. This can be simplified to half m maximum velocity squared multiplied by sine omega t. So the potential energy from the equation of potential energy that we derived earlier this lesson, and we put in the equation for displacement that we derived last lesson, and we end up with half m omega squared amplitude squared multiplied by cos omega t. Now that we have equations for kinetic energy and potential energy in terms of sine squared and cosine squared, it might be a little bit easier to understand why the total energy then equals to a constant value by looking at Pythagoras, where if we end up with cos squared theta plus sine theta on a unit circle, it gives us a solution of 1. That's it for today's lesson. Hope you found it useful. You've got the worked examples coming up. Remember, pause it, try it on your own. If you get stuck, press play and watch the video. Thanks a lot, and see you next time.